Honshu is the largest of the three major Japanese islands. The Tohoku region of northern Honshu has three prefectures on the Pacific coast directly facing the Japan Trench. At this subduction zone boundary, the Pacific Plate descends into the Japan Trench and beneath the Okhotsk Plate at 8.3 centimeters per year. On March 9, 2011, a magnitude 7.3 earthquake started a series of foreshocks. The magnitude 9.1 Tohoku Oki main shock occurred just after 2:46 p.m. local time on March 11, 2011. It was followed by hundreds of aftershocks. This great earthquake and the resulting tsunami took almost 20,000 lives and caused approximately $200 billion in damage. Scientific lessons learned and described here include tsunami geology is critical to assessing earthquake risk. Earthquake early warning can save lives and decrease damage, but the 2011 earthquake revealed limitations of a system using only seismometers. Adding global positioning system observations of earthquake ground motion can improve earthquake early warning and is essential to tsunami warnings. Tsunami monitoring has advanced rapidly in recent years, and the seismology and geodesy lessons from the 2011 Tohoku Oki earthquake are being applied to earthquake and tsunami warning systems worldwide. However, these technical advances are necessary but not sufficient to advance earthquake and tsunami preparedness. Public education is essential, and often the most basic lessons are the most empowering. During an earthquake, drop, cover, and hold on. If you are near the ocean, the earthquake is your natural tsunami warning. Move quickly away from the shore to high ground as soon as you can move safely. Now, let's dig into the plate tectonics and earthquake history. A cross-section through the March 11th epicenter shows the Pacific Plate subducting beneath the Okhotsk Plate. The megathrust plate boundary extends from the Japan Trench to a depth of about 120 kilometers. Before 2011, what observations did we have about earthquakes on this megathrust plate boundary? For each earthquake of magnitude 7.4 and larger between 1896 and 2010, the year and rupture area of the plate boundary that moved during the earthquake are shown here, along with the earthquake magnitude. This history suggests that earthquake magnitudes might not exceed 8.2. But research in the decade before the Tohoku Oki earthquake led some seismologists to conclude that an earlier earthquake with magnitude of at least 8.4 had caused a massive tsunami that inundated the Sindai Plains. Geoscientists found a sand layer they interpreted as having been deposited by that tsunami. Historical documents revealed that this earthquake and tsunami occurred in 869 AD. This geologic evidence suggested the subduction plate boundary could store elastic energy over 1,000-year intervals, then release that energy in a megathrust earthquake of magnitude 8.5, or perhaps even up to magnitude 9, 25 times more energy than any earthquake in the region since 1896. How could they test their hypothesis that elastic energy was being stored? First, seismologists determined that motion between the Pacific and Okhotsk plates during earthquakes of the past few centuries was much less than the relative plate motion. Did that mean that plate convergence was mostly accommodated by compression of both plates across a megathrust boundary locked by high friction? In fact, high-precision GPS monitoring across northern Honshu from 1990 to 2010 showed stations being pushed westward at up to 3 centimeters per year. This compression of the overriding plate stores elastic energy similar to a spring when the coils are pushed together. Although we can't measure it with GPS, a similar compression occurs within the subducting plate, and most of the relative motion occurs as compression of the plates across their high friction boundary. So, this subduction zone could store elastic energy over many centuries, then rebound during a massive earthquake, as it did on March 11, 2011. Rupture started 24 kilometers beneath the seafloor at the hypocenter, then propagated both up to the east and down to the west. The amount of fault slip was determined from GPS motions on land, seismic data, and surveys of the seafloor before and after the earthquake. Fault slip of 40 meters at the hypocenter and over 60 meters at the Japan Trench are the largest documented for any earthquake in modern history. The 40-kilometer-wide seafloor slope west of the trench uplifted 10 meters, while the seafloor near the coast dropped 2 meters. These offsets of the ocean floor produced the tsunami that began arriving onshore 30 minutes after the earthquake. Inundation height reached 20 meters on the Sendai Plain, the most populous area in Tohoku. Tsunami run-up in some locations reached 40 meters. Fatalities, plus the missing, concentrated in Iwate, Miyagi, and Fukushima prefectures totaled almost 20,000. In map view, fault ruptures spread from the epicenter to cover an area 500 kilometers long by 200 kilometers wide in just over 2 minutes. Fault slip was greatest between the epicenter and the Japan Trench. Despite minutes of strong to severe ground shaking, fewer than 50 fatalities occurred outside of the tsunami zone. Centuries of experience with earthquakes, world leadership in earthquake engineering, stringent building codes, and quality construction practices saved thousands of lives. Japan's earthquake early warning system also decreased impacts of earthquake ground shaking. The earthquake early warning system, in place prior to the Tohoku-Oki earthquake, used a dense network of broadband seismometers that detect P waves from an earthquake, locate the epicenter, estimate the magnitude, and then provide warnings before potentially damaging S waves and surface waves arrive. This works reasonably well for magnitude 6 or 7 earthquakes within or near the seismic network. This was not the case for the March 11th quake. 22 seconds after the earthquake rupture began, P waves reached seismometers on the coast. An early warning was issued to advanced users at 30 seconds and to the public at 31 seconds, 14 seconds before strong shaking arrived in Sendai. Numerous protective actions were taken, such as slowing trains, alerting fire, police, and emergency personnel, and alerting hospitals, and those measures decreased damage, injuries, and fatalities. A warning system based on broadband seismometers can notify you that an earthquake has occurred, but it cannot rapidly determine fault slip or final magnitude. Even when rupture was nearly complete, magnitude was estimated at a magnitude 8. As a result, tsunami alerts issued at 3 minutes badly underestimated wave heights. To make matters worse, power outages limited communications. How can we improve these earthquake and tsunami warnings? Installation of GPS networks and advances in the precision and speed of receivers has led to the integration of GPS and seismic networks. GeoNet in Japan is a leading example. As more and larger earthquakes have been recorded by GPS networks, the power of combining GPS with seismometer observations has emerged. The 2011 Tohoku-Oki earthquake is the case study. During the earthquake, GPS stations across northern Honshu moved toward the area of greatest fault slip by as much as 5 meters. For example, station 0172 moved 2 meters south and 4 meters east between 50 and 100 seconds after the megathrust rupture started. A network of seismometers alone, such as used by the earthquake early warning system in 2011, cannot determine a fault slip model for a great megathrust earthquake or accurately forecast tsunami wave heights in time to issue useful tsunami warnings. Several research teams have shown that combined seismometer and GPS ground motion data could be analyzed to determine a reasonably accurate fault slip model for the Tohoku-Oki earthquake within 90 seconds from initiation of rupture. Installation of the SNet cabled system of ocean bottom seismometers and pressure gauge stations has taken subduction zone earthquake and tsunami monitoring a giant step further. With instruments on the ocean floor directly above the plate boundary megathrust, SNet can provide earthquake early warning 20 to 30 seconds sooner than land-based networks, and measurements of tsunami heights in the source area can provide accurate tsunami forecasts more than 30 minutes before a tsunami reaches coastal communities. A primary scientific lesson learned from the 2011 Tohoku-Oki disaster is that combining seismometer and GPS ground motion observations can improve speed and accuracy of earthquake and tsunami warnings, especially for great subduction zone megathrust earthquakes. Indeed, a new scientific discipline of seismogeodesy is emerging from this combination. Still, the most basic and important preparedness lessons remain. Drop, cover, and hold on during earthquake ground shaking, and if you're near the ocean, move quickly away from the shore to high ground as soon as you can move safely.